Good day, ma'am. So this is how I solve the two following problems given on the topic soil permeability and seepage. So in problem number 1, our given is that find the rate flow in or the flow rate in cubic meter per second per meter at right angles to the cross-sectional shown in the figure through the permeable soil layer, given that H is equals to 4 meters, the H sub 1 equals to 2 meters, the small letter h, which is equals to 2.75, this distance from here, the s, that is 30 meters, that's the alpha of the angle, that is 14 degrees, that is considers that is what is mentioned here as the right angles in the cross section, and the k, or the hydraulic conductivity, that is equals to 0.075 centimeter per second. So since we have this given by proper designation of the values from here, I did manipulate the problem easily and smoothly. So h here, this is the h, this is the 4 meters, the h sub 1, this is the 2 meters, this dimension, and this h here, the small letter h here, that is considers the height, this is 2.75 meters, the distance. This right angle here, that is actually the opposite. This is the angle, the angle alpha, that is 14 degrees. Then our hydraulic conductivity, that is equals to 0.075 centimeter per second, is constant. So in order to solve this problem, I use the formula or the situation. So I consider the hydraulic gradient I, that is manipulate the equation, that is h over L over cosine alpha. So I manipulate the equation from here, so it resulted to that I is equals to h cosine alpha over L. So from equation 7.18 and 17 from the book, so this is the formula in determining the flow rate of the water, the rate of flow of the water. So that's Q is equals to K over K, that is the hydraulic conductivity, times I, that is the gradient, the hydraulic gradient, times the A, our A here, that is the cross-sectional area, and the cross-sectional area, that is equals to, so since we have the values for this K, and just substitute this the equation of I from here, that is I, that is equals to h cosine alpha over L, times the area, that is h sub 1 cosine alpha times 1. So we have the given, and just substitute the given, that is 0.075 times 10 raised to 2 negative 2 multiplied by 2.75 cosine 14 divided by 30, that's the L or the S, times 2 cosine 14 times 1, that gives us the hydraulic flow of the water in decimal form, that is 0.00129 cubic meter per second per meter, or in exponential form, or in scientific form, that is the rate of flow, that is equals to 0.129 times 10 raised to negative 3 cubic meter per second per meter. So in problem number 2, the figure shows 3 layers of soil in tube that is 100 by 100 mm in cross section. So water supply to maintain a constant head difference of 300 mm across the sample. So this is the 300 mm, this is a constant head difference. The hydraulic conductives of the soil in the direction of the flow through them are shown below. So this direction of the flow, the direction of the flow. Then find the rate of water. So my mission is to find the rate of water supply in cubic centimeter per hour unit. So given that we have this figure that shows the direction and the designation of the values given. So we have the hydraulic conductivity given for different variations of soil, that's soil A, B, and C, that they also have dimensions. So there's a cross-sectional, they have cross-sectional dimensions. So A has a cross-sectional dimension of 150 mm with a hydraulic conductivity of 10 raised to negative 2. our soil B, we have still 150 millimeter with hydraulic conductivity at 3 times 10 raised to negative 3. And so with soil C, that is 150 millimeter with hydraulic conductivity, that is 4.9 times 10 raised to negative 4. So in determining, we have to first determine the equivalent hydraulic conductivity. So determine the general. So I can term this as the general hydraulic conductivity. That's to equate them into using this formula, that is equals to H over H sub 1 divided by K sub 1 plus H sub 2 divided by K sub 2 and H sub plus H sub 3 divided by K sub 3. So substituting the values, so how did I get the values for H? Is simply to add all the cross-sectional dimensions at soil A and B, that is 150 plus 150 plus 150, or simply 150 times 3, since there are 3 soils, or 3 soils. So variation of soils, that is, we have 150 times 3, or 150 plus 150 plus 150, is 450. That's the total H, divided by 150 times respective hydraulic conductivity for H sub 1, 150 divided by 10 raised to 2, is actually negative 2, plus 150 divided by 3 times 10 raised to negative 3, 150 times plus 150 divided by 4.9 times 10 raised to negative 4. So we'll have the equivalent, or the total hydraulic conductivity K, that is equals to 0.001213 centimeter per second. So again using the same formula in getting the flow rate of water as I have used in problem number 1. The only difference is that we get the value, or the total value of the hydraulic conductivity from here, given that we have different different types of soil. So with this, just substitute this value, that is 0.00123 multiplied by the I. So our hydraulic gradient, that is the H, that is the constant head. Yes, the constant head divided by the H. So I can treat this as a small letter H, which is equal to 300 millimeters, because that's the constant head. So divided by 450, that's the total the H, the total H, this total H, that times the quantity of 100 over 10 times 100 over 10. So simply it is divided by 10 in order to have a result of meter per second, or cubic centimeter per second. So just calculate this using calculator. So you have 0.0809 cubic centimeter per second. So since the mission is to solve it in terms of cubic centimeter per hour unit, so we just have to convert it by multiplying the 0.0809 cubic centimeter per second times 3,600 seconds. That is the equivalent seconds per 1 hour. So in 1 hour there are 3,600 seconds. So multiplied, just perform the calculation, and then we have 291.24 cubic centimeter per hour unit. So that's how I solve the problem. Thank you.